Hey everyone, welcome back to another very exciting Unity VFX particle programming tutorial, and today we're finally going to be working on this Plexus effect that you see here right now in the background. For this, we're going to be creating a new component, a custom particle system component that we're going to program ourselves called Particle Plexus, and this is based off the After Effects plugin by the same name known as Plexus, where what basically happens is you have these individual particles and the particle looks around itself, checks to see if there's any other particles nearby, and within some distance that we specify, such as max distance right here, if there's a particle, it makes a connection to it. So we've got a bunch of parameters we'll be able to play with once we're done the entire tutorial. You know, for performance, we've got max connections, maximum of line render as possible, the width, wherever you want to get it from, either the template you pass in or the particle itself, you know, the color from the particle, or the template, you can lerp between them, and also this wacky delay effect, which almost makes it look like it's lagging, but obviously, as you can see, it's otherwise just fine. So that's for the full tutorial, but today we're actually going to keep it a little bit simple and instead just work on this, right? So this is a simplified component that we're going to work on, and in the next episode, we'll add in those extra parameters. So you can see we've got max distance, max connection, line renders, and then the template. So without any delay, let's get started. So obviously the first thing I need to do is create a new C# component. I'll call it Particle Plexus 3. You can just call it Particle Plexus because, you know, I've got other copies in here, so I do need to add in the extra thing. Open it up in Visual Studio. So at this point, I just want to remind you guys that if you haven't watched the previous Introduction to Particle Programming tutorials, you should do that because we're basically just building off of whatever we made there, and a lot of the concepts are similar, so I won't go into them in as much detail. So with the Particle Plexus 3 script component just created, I'm just going to quickly take this out because I know I won't be needing this namespace, but I will be needing this for lists when we get to that later. I'm going to add a require component to this type of particle system, so we know that there's a particle system component attached to whatever object this script is also attached to, because we will be working with that, and we're going to be doing everything inside of late update and start. I obviously also want to start creating a public float for the max distance, which equals 1 in this case. I'll get the other two in a bit, which is max connections and line renderers, and then I'll just quickly skip ahead to particle system, which is the reference to the particle system on this game object, as well as saving, and I'm using new because of the old, I don't want to conflict with the old Unity 4.x stuff. Particle system dot particles. So this is an array that contains all the particles in this system that I'm going to save outside here. And I'll also save the main module, although it's not going to be a huge performance boost, right here, just for the heck of it. Okay, so in start, I need to actually get the component, which I can do like so. Particle system equals get component, particle system, and also the main module, which I can get off that system, equals particle system.main. So now that I have that, I can move on into the loop here. I'll do int max particles equals particle system main module dot max particles. So we need to make sure that if particles array has not been initialized at all, then we need to first set it to the max value, the max particle count size. So particles equals new array of size max, particles of that length, and then we also need to make sure that if the array or if the max particles value ever changes to be greater than the array size, then we need to adjust the array length as well. So particles.length, if it becomes less than max particles, then again reallocate the array. So now we can move on to our main loop. So now what we need to do is get all the particles in the system and then throw it in this array right here. So we can do that by doing particle system get particles, and I'll get as many particles as are in the system up to whatever the size the array is. So in this case, because the array size is greater than the number of particles we can get, it shouldn't be a problem filling it all up. Then we create an int particle count equals particle system dot particle count. So now if we go to the main loop, we can do an int for int I equals 0, I is less than particle count, I plus, and that'll just make sure that we go through every single particle in the system, and then we need to duplicate this array create a second nested array using J. Basically what's going to happen is we're going to compare every single particle, its position, to every other particle's position and see that if it's less than max distance, then we'll create a connection between the two. So for this, we don't actually need to start at 0, we can start at I plus 1, because we know that for the previous particles checked, if it found a particle position or another particle that was close to it, it's already made a connection to that particle, and we don't need to double back and check the connection again. It also saves up on, obviously, performance, because we're not creating two lines between the two of them, and also not checking every single particle against every single particle. We have a little bit of slack here. You can use better algorithms for this, you can use partitioning and whatnot, but because this is what I'm familiar with, this is what I'm going to be covering in the tutorial. So how do we do this? Well, first, we need to create a vector 3 for the first particle's position. I'll just call it P1 position for particles I dot position, and then get the position of the second particle as well. And now I need to get the distance between the two. So what I can do is float distance equals vector 3 dot distance between the first particle and the second particle. Now this is fine, it'll do what we want, but the problem is that distance is actually a pretty expensive function call because of what it does inside. So what it does is that it basically gets the difference between these two, and from that vector it calculates the magnitude, that is the length of the difference vector, and then that gets the distance between the two positions. So that's fine, it is what we want, but it's expensive because it has a square root call in there. So we can just directly call magnitude and subtract these two. So again, this is equivalent to distance, but we can make that better because instead of doing magnitude, which does the square root call, we can do the square magnitude, which doesn't call square root, and then call this distance squared. And then instead of comparing against max distance on its own, which has a default value of 1, which is just 1 meter, we can create a new variable right here, float max distance squared, and it's outside of the loop, so it's not a big deal to add that extra multiplication in, multiplied by itself, and we can just compare it to here. So if we do if distance squared is less than or equal to max distance squared, we know that this second particle that we're comparing the first particle is within this particle's range, so we would create a connection inside here. So at this point, we need to go back to the line renderer stuff. So let's go up here and create a new public line renderer variable, which is the line renderer template. And I'm going to be using this word line renderer over and over again, so it's possible I might start pronouncing it weird and, well, just weirder as time goes by. So list, and we want to keep track of all the line renderers that we create so we can reuse them. So we'll call it line renderers equals new, we're just instantiating here, and I think that's good to go. So for this, we also need to create another variable out here, which keeps track of which line renderer we're working with so we can reuse them properly. Now, because this is a list, I want to keep track of the count myself rather than constantly calling the count on the line renderer variable. So what I can just do is quickly create an int line renderer count here, which is just line renderers dot count, and I can modify that value after if I add any more or whatever else. So what I can do is, if the LR index is equal to the line renderer count, we know that the line renderer count is the number of line renderers, not the index, and the index is an index which is a 0 index, it starts at 0. We know that if this is 0 and the count is 0, then we have one more line that we need to have more than whatever this is, right? So that's just for the first one. If, for example, this was 27 and the index was 27, we know it's the 28th line renderer because it's a 0 index. So we know that if they're equal to each other, then I do need to create a new line renderer. So what I can just do is line render LR equals instantiate based off our template. Okay, we use the transform and we want it to be parented to this transform, and then we add false for world space. Now we can actually cache the transform out here, call it transform, and then just keep a reference to that somewhere like this, equals transform, and then just use that one. So that way we're not accessing the property of this game object for the transform. And then we can just add it to the line renderers that we have. So add this one. So now that we know that that line renderer exists, we can just go ahead and set the values for the position for this line renderer, which is LR index dot set position 0 to the first particle position, and then the second one to the second particle position. Make sure to add 1 here, so it's the first and second position. So this line would be like from here to here or whatever else, wherever the particles would be. And that's close to finishing off our template. Now I just need to quickly increment the line renderer index as well as the line renderer count because we've added a new one, right? So I can just do that. Now outside of this for loop, I can just quickly create another one, I equals LR index. And what this is basically going to be doing is making sure that any unused line renderers are disabled, so they're still, if the particle count changes, then they're not going to be rendered and they're just going to be disabled. And we can know that based on the LR index because the LR index is the number of line renderers we've actually used. And if that number of used line renderers is less than the actual count of line renderers, which I can just use this for, then I can disable all the extra line renderers from there on. So I can just do line renderers I dot enabled equals false. Okay, so now that we've also disabled them, we need to remember to also enable the ones that we want to use. So we'll go here, set this to enabled equals true. And I realize that this should not be I, this should be J because it's the second particle position. So one thing I want to mention now at this point is that getting an element from a list is actually pretty expensive. So what we can do is just save the element beforehand. So here I'll just copy and paste this above, and then I won't need to do that, and then I can do LR equals the current index, and then just use LR for the rest of the stuff. So like this. Okay, and I think that's all we need to do to actually test this out. Okay, so to be able to test this, I need to first create a line renderer template, so I can press Ctrl-Shift-N to create a new game object, or just do it from here, create empty. Make sure it's completely reset, and then add the line rendering component. I'm going to leave everything to its default value except the material, which you can use the default material. I'm going to use a material from my Ultimate VFX particle pack. I'll leave the link in the description, and I'm going to set the width to 0.025. I'm going to keep world space, and I'll show you why that may or may not be a problem shortly. So I need to just rename this quickly to line renderer template or something, and then drop this into my list of prefabs, and then delete this object because I don't need it there. And then make sure also that the positions, the number of positions is set to 2, because obviously here we don't modify it. So with that being said, I can just pass this in and hit play, and it should work. So you can see that it's working, but the positions aren't quite right, and that's because I set it to world space enabled, right? That was the default value, and it's also instantiating a ridiculous amount of line renderers because there's no limitation set up right now, which we'll do shortly. So let's disable the world space, use world space on the template and see what happens, and the positions should be corrected now, right? So the reason that happens is because right now I'm using the simulation space set to local, which is a mismatch between what the line renderer is being rendered in. So the positions that are being passed to that aren't in tune. So let's play this again with world space simulation this time and world space on the line renderer, and you can see they're in sync. So we can actually make sure all of that works in the script itself. So to do that, right about, let's say here, I'm going to create a switch statement and check the particle system's main module simulation space. So particle system main module dot simulation space, then create a case for local. Okay. Break that. Create a case for custom, and create case for world, and then finally create actually a default case, in which case we should throw a new exception. So system not supported exception. We'll do string dot format unsupported simulation space. Pass the parameter, let's put a period there, comma, system, ration, get name, type of particle system simulation space, particle system main module simulation space. I need to add maybe one more of this, and I think that's good. Okay, so I'll just drop this down here so it's neat. Okay, so for this transform, we can actually take this out because we won't be using it here, but rather it needs to be here. So the transform in the case of local is the same transform as this. In the case of custom, it's actually the custom simulation transform. So we can use custom simulation space, which is a transform, and in the event that it's world space, well then we can just pass in this again, right? But we do need to modify the templates world space variable. So what we can do is just get the template, set use world space to false, false, and true for this one. And that should allow us to switch back and forth freely between the simulation spaces. Oh, I missed something. There we go. So this is fine. You'll be able to switch between the simulation spaces as long as you don't do it in play mode, because if you do it in play mode, it's only going to get some of the newer instantiated line renderers, and it's going to miss the ones that have already been instantiated with the settings preset beforehand on the template. So for example, if I move this up now, it's fine, but let's say I set it to world space, it's not going to work anymore unless it instantiates more particles, and it gets all messy and weird. You can see it's instantiating up there, or it's moved the systems up there. So what we can do is, and it's up to you if you want to do this because it does have a small performance penalty, you can just save this simulation space first of all. So let's create a new here and call it simulation space. And we can instead set it for every single line renderer every time we render it out or cycle through it. So simulation space equals, so that's the current simulation space for the particle system. We can just use this now. And instead of setting it here, okay, we can just, I forgot this. We can just do it right here somewhere. So we can do line renderer use world space equals simulation space equals world. Yes, no, if true, then set this to true or false. Another way, this is fine because it's used up here. So that's fine. We could also do something similar here. I doubt Unity again is gonna be adding more types here, so we could have just used something similar up here, but for now I'll just leave it as is and let you guys figure out if it's worth changing. So if I go here now, I should be able to switch it while it's playing without any issue. So again, if you think that's okay, it's not gonna be too big of a deal for you and you want that, then go ahead and implement the rest of that code that I just did. So we can switch back and forth between world space, right? It's all good. Okay, so with that out of the way, there's only a few small things left to do, namely the limiters, right? So right now it's just getting it's just instantiating line render after line render, and there's no way to stop that. So we need to create a new public int max connections equals, let's say, a default value of 5, and we'll also add a max number of line renderers. And we'll set that to maybe a value of 100. So what we can do now is, first of all, only execute the majority of this code if both of these values are over 0. Because if any one of these values is 0, then we know we're not actually going to be rendering anything. So we can just save up and say, hey, listen, if both of those values are 0, don't execute all of this expensive code. So we'll do that around, let's just find a good spot. That can be put, okay, so we'll keep this. We don't need to get the particles in this case. We will need the line renderer index for this code here, which won't be inside. So we'll just move the line renderer index here and we'll do it here. So if max connections is greater than 0 and max line renders is greater than 0 as well, then and only then should you be doing all of this expensive stuff here. I don't think I missed anything. Do I need all of this here? I guess so. We'll leave that out there. So we have that first of all set up. We also need to monitor the number of connections that we make. So we can do that here. So we can do int connections equals 0. And after that, we need to check right here and add connections plus plus because we've made another connection, and this will always be reset to 0 on every loop for the single particle that's being compared to the other particles, and then that way we know how many connections for only that particle have been made versus the entire number of line renderers. So if connections equals the max connection value, or if the LR index is equal to the max line renders, then we break out of this loop. We also need to put another check here right after we do, right at the beginning of the thing, for the max number of line renders, and we'll break out of the second loop as well if this has been reached. So I think that's good. Oh, I missed that one. Okay, so I should have put this outside as well. Somewhere here, probably. And that's just useful for that. Okay, so now we have the limiters in, and we can hit play, and it should be much more performant because it's not going to be having a ridiculous number of line renders. You see, that's much better, right? Now what happens if you want to decrease the maximum number of line renders? Well, the ones that you instantiated are still there, which may be not an issue for you. Maybe it's fine. But in my case, I'm actually going to destroy them. Again, this is optional. You can figure out if you think it's worth it to get rid of all those extra game objects that are in the scene, or if it's just a waste of time and you'd rather just have the performance. So in this case, I'm going to be implementing if line renderers dot count. Actually, again, this can just be underneath this part right here. If line render count is greater than the max line renders, then for int I equals 0, I is less than line renders and render count, I plus plus destroy the game object for all those line renders. And then we need to remove them from our list as well. So line renders dot remove range from max line renders to line renders. Hate saying that word so many times. Count, in this case would just be this. Basically, starting at this index, remove these many, the difference between the two basically, right? And then what I can do is, now that we removed the difference between these two, I can also reassign the line render count to be the difference. Or we could just save the difference, so it'd be like int removed count equals the difference here, and then removed count, and removed count. And that's good as well. So let's hit play and quickly check that out, and that'll conclude the tutorial if everything works. So here it is, not a problem. Let's decrease this. Uh-oh, I ran into a problem. So let's see what's happened. This should be max line renders right here. So let's hit play again. Okay, looking good so far. We can set this even to a negative value. And then of course it creates a problem, but once we have maybe like, let's put like 4 here, see what happens. So 1, 2, 3, 4, right? So this works. You can just limit it to make sure it's not less than 0. But otherwise, you can see everything seems to be working. And in the next part of this tutorial, we'll start implementing this final stuff right here, like the width from particle, color, and whatnot, so that way you don't have to use the color from the template, which you can do as well. So for example, if you wanted the template to be maybe going from yellowish to red, you could just set that up here. And if you want it to be thicker, you can also make this 0.05, so it'll be double the size. And you know, that's what happens, right? So now what we're going to do is basically be changing those. In the next tutorial, we're going to add parameters to change those from script rather than having to specify it in the template. So we can also make this maybe 1,000 so they're not constantly jumping around. Let's see what happens. Set the max connections to 1 to test that out. Now you can see they're only making 1 connection per particle. And I think that's pretty good. All right, so thanks for watching, guys. Please subscribe, leave a comment, and a like. If you want to let me know what else you'd like to see, if you need clarification, you know, just let me know in the comments, ask away, I'll be happy to answer. Thanks for watching, and I'll see you guys next time. Bye.